This is dubious code with Project Euler 3 in Python. So find prime factors of numbers, basically. So here's an example of some, I don't know, 6 billion, 600 billion or something. And the prime factors are 13,000 and change, 5, 7, 13, 29. I think there's two things here. One is you have to factorize the number. And second, you need to get primes. So I think starting with a list of primes isn't a horrible thing. I'm not sure it's the most efficient, but what is this up to? This would be thousands, millions, 600 billion, prime numbers up to the square root of 600 billion. What is the square root of this? It's less than a million, so why would we be finding all prime numbers less than a million? I think that should be relatively fast. So let's just start with a function of find all primes up to a number, and then we'll see which of those are factors. So, of Euler, def, find primes. Is this? I can't remember. Is Python? I don't know. I'll do snake case. Primes up to. Probably not. Probably primes up to n. So this is going to be a prime sieve. So primes equals 2. Start with a list that has 2. For let's see. For I in range 3 to n plus 1 by 2. Now let's see. For prime and prime, so we'll loop through all the previous primes. If prime times prime is greater than I, break from this loop because we've hit we're greater than the square root. Is prime equals true? We'll assume it's prime. Well, this would be true if I modulus prime equals 0. Then it's not true. Is prime false, and we'll break. Are there any other cases? So this is be a not prime, and this is the end of the loop. And if it's true, if is prime, primes dot append I. So let's start with seeing that if that will work. We say primes up to 10 equals primes up to n. We'll start with 20. And we'll say print primes are. We'll just print the primes. Print the primes. And this will be Euler 3. So we'll clear the previous one. Pi Euler 3 dot pi Euler underscore 3 dot pi. All right, what did I do wrong? Semicolon instead of a colon. None. Because I didn't return anything. Return primes. Okay, so less than 20. Up to including 20. So let's see what we got. 2 is prime, 3 is prime, 5, 7, 11, 13, 17, 19. I know these are prime just from enough time with numbers, so that appears to be working. Let's see what our target number is. Our target number is 600 billion. Let us go to SQRT equals, better import math. Math. Uh, 0.5, take the square root of that, and we'll take the integer of that. Int square root. So we only need to go up to that. Print. And now I'm just curious. I don't need to list them all, but I'm just curious if this is going to run in a reasonable time. And let's see how many there are. Length. Is this going to run in a reasonable amount of time? Okay, that was a couple seconds. There's 62,000 of them, which is fine. So we have primes, and now we need to get prime factors. So let's say factors equals prime factors equals find prime factors of this guy. And we'll make a function def find prime factors and of target. And this stuff can go in this function. So we're going to call, first get the primes. Then there's probably a better way to do this. I was going to loop through all the primes. And then I was going to loop through the prime, just check the modulus. But that doesn't really take into account if let's say I get 2 first. I divide by 2. I'm going to go ahead and do that. It'll be a little bit slow, but it's not the worst thing. So wow. Okay, so prime factors. We'll start with an empty list. And remaining equals target. We'll start with that number. While remaining is greater than 1. And index. This will be the index of the index of our prime. So while remaining is greater than 1, if prime equals prime's subindex, this is the prime we're targeting. If remaining prime equals 0, if it's a factor, then we will say prime factors dot append prime remaining equals remaining divided by prime. Else, if it's not a factor, we look at the next prime, index plus equals 1. Okay, so this should account for if we have like a 2 and 8 would have 3 2s as a prime factor. So let's say, let's just check that. Print factors are str prime factors. So we expect here to see 3 2s as the prime factors. Factors are none. That's not ideal because once again, I forgot to return anything. Return prime factors. Factors are 2 2 2. That was a little bit slow. I didn't love that. I'm not sure why that was so slow. Oh, because we found the primes up to the target. We don't want that. We need to find it up to that target. We hard coded that 6 million. Okay, so that's a lot faster. That's good. Let's look at their example of 13195. We expect to get 5, 7, 13, and 29. 5, 7, 13, 29. Excellent. Let's try this 600 billion. All right, so 4 prime factors, and the largest one is 6857. 857. Okay, that's done with problem 3. My guess is that for my memory of doing Project Euler before, this is finding primes is pretty common and probably prime factors. So I'll just make these as a library function and I'll just use them over and over again, I imagine. All right, this is Dubious Code. Thanks for watching.